All right, now we come to a new lesson, and this lesson will describe one of these subgroups, the definitions and taxonomy subgroups. And this actually is meant to tell you what all these words mean. I pointed out that one of the problems with big data and also data science is that it's not so obvious that people agree what they are. And so they're trying to understand these big words and also to go into a little more detail about the components that are brought together in these concepts. And there's a very detailed, thoughtful analysis that will be published after this process goes through the technical editing and things like that. It will also not only looks at the words, it also looks at the stakeholders and the actors, and so that we can actually talk coherently with a common vocabulary across different architectures and different applications. And of course, the definitions and taxonomies require compiling ideas from various sources, trying to reconcile them and get some consensus definition. Taxonomies require making lists and making certain that all possibilities are covered, and then trying to put some hierarchical order on them in terms of components and subcomponents. Interestingly, I found it appeared to me there was more agreement on what data science was than there is on what big data is. So big data, as I said, is sometimes defined by the V's, of which the most common V's are 3: volume, velocity, and variety. And these, and the bigness is the bigness of this. So this says you can actually have a small volume, but if you have high velocity and it gets updated very quickly, or very rich variety, then it can still be effectively big data because the processing problem is big if you have a very complex data source. But as I say, I think probably more important than bigness is impact. Namely, is this data really allowing new approaches to critical questions which were not possible to do using traditional methods such as simulations or what you might call pure observation, the Newton's apple idea. And of course, the bigness comes when they need more data than you have on your disk system, or they need more computing than you have in your cluster. And of course, one of the reasons we have big data is we're able, through the internet, to get large populations of various data sources. And the management techniques need to scale. Namely, they have to have horizontal, means that you have a lot of things. You get increase in size, not by making each unit much bigger, each bigger and bigger, but by just having more and more units. And so you need to be able to manage this whole process with this scaling and the number of the units works out. So here is, so I think there was more agreement here than on that previous slide, a definition of data science. There is a picture which shows the various things are brought together in data science. There's research, there's application in the informatics, the X and X informatics, that's domain expertise. We have an analytics, and here we have the integrating idea of data science in the middle. Analytics involves algorithms and applied mathematics and convergence and rigorous things. This all is very closely related to statistics and data mining. They're sort of the same thing looked at from different points of view. And of course, all has to be programmed. So these are the types of skills that data scientists can need. And always in these interdisciplinary approach, always have this trade-off. When you need to bring 10 skills to a problem, do you hire 10 people, each with one skill, or do you have one person with 10 skills, jack of all trades or several masters of an individual trade? And probably you could say that to lead all of this, you probably better have a jack of all trades, because only a jack of all trades could bring this diverse group together. But if you have a big enough team, you're going to have specialists and generalists. The generalist being this um, idealized data scientist defined here, who has got sufficient knowledge of all these regimes and sufficient expertise in the final needs of the, well, here you see it says business needs, it could say science or research needs, and then it has to master all these circles on the right, and has to be able to do all of this. Now, that's a pretty good person to have, but my bet is that you don't have so many of those. And anyway, most of the ones you have will actually have a specialization. Maybe they're super good at analytics or statistics or whizzes at programming, but they might still have significant knowledge of all the, I mean, so you can have somebody who's very good at one of these circles or one of these regions, and pretty good at the rest. That's a data scientist. Here are the actors and the roles. Actors are the components we need to bring together to do a big data system. The applications, the software subsystems, the sensors, the people, the organization, the various services. I mean, he says service abstractions. An important concept of services are they have to have abstractions, because services are black boxes that receive information, data, and control, and give out information, data, and control. And to have an abstraction as to what that service does is pretty important in allowing people to have a service ecosystem where different people build different services, or different people compete to build the same service. If we look at the various roles, we have the provider of data, the consumer of data. These roles are not particularly people. They could have involved people, but they can involve computers and software and things like that. We have the orchestrator, which puts everything together. We have the application provider and the framework provider. So where the application provider, if you like, runs on the framework provider, or the framework provided by the framework provider.